Okay, so I'm going to talk about some thoughts about superconducting phases in metallic altermagnets. By the way, altermagnets, I call them the alter states of magnets. As alter states of minds. I have to crack that joke sometime. Okay, this work with Xuan Zhou. She was a student, a visiting student from Tsinghua. She was in Urbana for a year. She's back in Tsinghua. And one of these days she may be able to come back to the US, who knows? And with Rafael, who you know is here. Okay, so this is going to be low. There will be very few equations. There will be just one free energy. There will be no actions, no path integrals, in spite of my fame. And I will not tell you much about mechanisms. I hate the M word. So I am a person who likes to understand phases of matter, however they come. And then they have to discuss how they can be realized, and that's a different question. Okay, so let me tell you a little bit of my personal history on this, so how I came to think about these problems. So I come from high TC, okay, which is a very different problem. This is a strongly correlated system where band theory most of the time doesn't help you, okay? It gives you just a framework but little else. Okay, these are strongly correlated systems. And then we came to realize that in systems like that, you get unusual states which are often inhomogeneous, that break translation symmetries, and they also break point group symmetries of the lattice. And we gave it a name back a few years ago with Kivelson and Vic Emery, with the late Vic Emery. We called them electronic liquid crystal phases of the systems, and this is by analogy, because in many ways they present analogies with concepts of classical fluids, so in particular the nematic fluids and the smectic fluids, even though most of our systems actually are strongly coupled to the lattice, and that breaks some of the symmetries that otherwise you may want to have. Okay, so I'll comment on that. So we realized back then that there are many phases that you can get. You can get what we call stripe phases, which are essentially indistinguishable from charge density waves. They have the same order parameter. Okay, so they are the same sort of symmetry, the same sort of phase. Some may be conducting, some may be insulating. But other phases, which are translation invariant but break the rotational symmetry, in particular the nematic phase, made, I think, one of its earliest appearances. There was actually some earlier paper by Kivelson and Emery where it was mentioned. So we decided this was part of the grand scheme of that. And these are symmetries which are invariant under translations and spin reversal. Okay, so they are simple phases, but they break the point group symmetry in the case of a lattice model. And in fact, it is the simplest example of an electronic liquid crystal phase. This has been explored now in very many systems. Somebody asked if these things are realized in nature. The answer is yes. Okay, the most spectacular case is the two-dimensional electron gas in relatively high magnetic fields. It's not in the lowest Landau level, it's in the second Landau level. And by the way, I label Landau levels, or refer to Landau levels as, floors in civilized countries, not like the US that begins with 1. Okay? Okay, so there is always a controversy when people say the first Landau level, and then they say the second Landau level, and they say n equals 1. No, that's n equals 1 is the first Landau level. And then they want to say the first excited Landau level, okay? That's a different story. Okay, there actually, this is actually the first actually documented example of a nematic phase. It has a gigantic anisotropy. The resistance anisotropy in the cleanest samples, these are samples that have, these are essentially gallium arsenide based materials. The samples have a nominal mean free path, which is about 1/10 of a millimeter. So you can see it. And mobilities of the order of 31 million. So these are like ping pong balls, essentially. It's like, it's as clean as it gets, okay? And in those systems, you get a resistance anisotropy that in one direction, it appears to go essentially to zero, but not quite. And the other direction is very high, and the ratio is in the cleanest samples is as high as 3,500. Now that's in the resistance anisotropy. If you look at the resistivity, which is different, the ratio is about 27. It's still enormous, okay? Normally if you get, in most systems where, for instance, in the iron superconductors, where this has been explored, for instance, by 2 people present here, there are similar things, but the ratios are not as large as that. So if you get the ratio which is as large as 2, then you say there is a large anisotropy. Okay? And in those systems, the native anisotropy is a fraction of a percent at 1 Kelvin. Okay? So these are really, it's an ordering effect. It's spontaneous. It's not quite symmetry breaking because it's literally a 2-dimensional system, and the lattice is almost non-existent. It's not entirely true. It does break the symmetry still. But you have huge orientational fluctuations in that case. It was then discussed in the case of the cuprates. There was quite a bit of controversy in the case of the cuprates, but I think it's clear that in very underdoped cuprates, in YBCO, for instance, very close to where the dome ends in the underdoped side, you see essentially a very large pneumaticity present. And this was seen by people like Keimer and others, essentially. And on the other hand, near optimal doping, this was seen in Nernst effect, you see pneumaticity again. But the origin appears to be different. In one case has a magnetic origin, the other case has an electric origin, but they have the same symmetry. So these 2 phases are continuously connected. There should be no phase transition between them, and if there was, then maybe there will be a line of first-order transitions with a critical endpoint that you should be able to go around it. Okay, they are morally the same phase, but there are different mechanisms at work. Okay, the same story, yes? Yes. I was expecting somebody will complain. Okay.
Is the Nernst effect like from...
It's a thermoelectric effect, okay, the Nernst effect. Yes.
I thought the Nernst effect in these systems is from when above the dome, when the vortices become mobile.
It has nothing to do with vorticity. That's a myth. There was essentially no vorticity by then. Okay. Originally, people tried to explain that with vortex motion. No, it's not really due to vorticity. Okay. The vortice, essentially phase fluctuations are constant. Well, that's a separate question. Okay? But the point is that no matter what the origin is, okay, it's the same phase, breaks the same symmetries. And that's why I wanted to raise that question, because the moral of many of these phases that may be one way to skin a cat. Okay, so you can get to the same phase, but with different mechanisms depending on the range where you are, okay, of parameters, okay, say doping or other things. And so please keep that in mind. Other examples are these bi-layer strontium ruthenate, 3 to 7. There is a range of magnetic fields between 7 and 8 Tesla. This is work by Andy Mackenzie. So we wrote back in 2010 a review with a bunch of people, including Eisenstein and Mackenzie and several co-conspirator theories. And then there are many other examples nowadays, so for instance in the iron superconductors and so on. So these phases often appear to be intertwined in the sense that the critical temperatures are comparable. When you suppress one order, the other one comes back up strong. So in a sense, this doesn't require to be close to some complicated multi-critical point. We don't really have a microscopic theory that explains all of this because it's all strong correlation physics. Okay, so this is phenomenology, okay, and I want to emphasize that. Now, on the other hand, these nematic phases, as is the case often in the, for instance, in the iron superconductors, they realize as vestigial phases, as partially melted phases where we have a phase that, say, breaks translation symmetry. You may restore the translation symmetry, but remember that you have an orientational symmetry. Okay, so the nematic phase, for instance, in barium arsenide, iron arsenide, is of this character. Okay, so this is that's also important. So there are two different ways of doing this. Now, I want to come back. So the way we approach this problem, so there was a paper that was cited by a number of people that I wrote around 2001 with Steve Cubenson and Vadim Oganessian, who was a student of his at the time, where we use a Pomeranchuk approach to access this phase. Now, Pomeranchuk, you have to keep in mind, is not a weak coupling instability. It's a strong coupling instability of a Fermi liquid. You don't get easily into a Pomeranchuk instability. Okay, so keep that in mind. Even though we have some nice bands and Fermi surfaces and all of that, to get there, you need to have strong correlation physics to begin with. Now, the same phase could be approached essentially by melting a stripe, and they are all in the same phase. So sometime later, a former partial student of mine, Kong Jong-woo, he started with, as a student in Urbana with me, and sometime in the middle he said he needed to go to Stanford and become Suchang student because he wanted to go back to China eventually. And I said, well, you can go there, you can graduate and go there as a postdoc. No, I have to be his student, he said. Okay, well, he was. And one of the things that they did is they postulated a P-wave version of a nematic state, essentially. So they included the effect of spin, and that's because this is the time where Suchang was interested in spintronics. And if you assume that you get into a phase which is sort of Rashba-like, if you wish, but comes from ordering, then it's not parametrically weak, as it is usually due to essentially in the Rashba scenario, because it's a relativistic correction effect. And so these are weak effects. In this other case, they will be strong effects. Okay, but the price you pay for that is to go through something, some strong coupling phase transition. So it turns out that the P-wave state they postulated in that recent continuum was unstable. It was unstable to the formation of spirals. And you can only stabilize it by adding spin orbit explicitly. Okay, so we joined together and decided to study this more generally. We understood that the P-wave, so again as an instability, as a Pomeranchuk type, so we use Pomeranchuk as a crutch, okay, as a way to access a phase, not because it's a weak coupling state. So we looked at the D-wave case, nowadays known as the altermagnet. And in fact, we were not aware, well, I should have been aware, but I forgot, that Gorkov and Sokol had similar ideas. They had a nice paper which, I don't know, it wasn't very easy to read to me. I mean, it was very easy to interpret. In hindsight, I understood what they wanted to say. Okay, so back in '92, they had a discussion of this problem, and we discovered much, or rediscovered many of these things. There's a long history of this. This is the altermagnet reference that I normally give by 3 characters for here. I think probably there should be some earlier reference about 2020, but I don't have that reference. This is the one, is a review of that. And we wrote this review. Actually, the other day, somebody, I think who was Libor, had a reference, and there was all of our names. And there was a reference to somebody named Newton, having worked on this. And I didn't realize that Newton had worked on this problem. All right, so Newton is a name of a journal that should not exist, but exists.
They're recording that.
I know they're recording, I don't care. Okay, so these are essentially the spin triplet versions of Pomeranchuk, okay? So imagine in that case you have some angular momentum, let's say L, and you are going to have essentially a phase transition, and we found two types of phases. With great creativity, we call them alpha and beta. Essentially because these are particle analogs of A and B phases of helium-3, okay, of the A and B phases of helium-3. But these are in the particle Hall channel. They are not superconducting, okay? This is different, okay? So the alpha phase is the altermagnet in the D wave channel, which is L equals 2. Essentially, the upspin Fermi surface distorts one way, and the D wave, the other one in the opposite way. And we had, so this is a collinear state, okay? So actually, with Steve Kevelson and actually with Vadim and others, we call the version of this the nematic spin nematic. It's sort of a joke, but essentially because it's not, by the way, the term spin nematic, I think this came up yesterday, is something else, okay? There's something called a spin nematic, which appears in frustrated systems in particular, and the order parameter is a triad, okay? You cannot write it in terms of a moment, so it's a triad, okay? So it's a different story. So it's nematic in the sense that it breaks spontaneously rotational symmetry in space, whereas a triad doesn't have to do that. It's all in the internal space. Now, I have to be careful here between real space and internal space, in particular when you break rotational symmetry. At the quadratic level, the order parameter looks like some global symmetry. It looks like an internal symmetry. This is a problem that has been well studied in the context of liquid crystals. Okay, in particular of nematic liquid crystals, that's formally, so they have an order parameter that is called a director. It's like an arrow without an endpoint, okay? And so you can think of the angle as an internal symmetry, but in reality it's a symmetry in space. So it actually couples to actual rotational symmetries. At the quadratic level in derivatives, you don't see that. If you include the quartic terms in the derivatives, you do see that, in fact, there is a relation between this internal space and the actual physical rotation space. In the liquid crystal literature, sometimes this is referred to by people like David Nelson, for instance, as a spin orbit-like effect. It's not spin orbit in the usual sense, but it's something that relates the internal space with embedding space. Okay? In that sense, it's similar. Yes, right. No, but the point is, even if you just take the nematic alone, there is this issue. Yeah. Is that an internal, sorry, the director, you can think of that as an internal symmetry, but it isn't, okay, because it actually knows about the actual rotations in the physical space. Okay, so that's important to keep in mind. So some of the symmetries, because of that, you need to take them with a grain of salt, what they actually mean. So then we have this other phase we call the beta phase, which is non-collinear. And for instance, in the D wave case, the Fermi surface splits, and there is a relative polarization between these two Fermi surfaces, and the polarization winds twice around the Fermi surface. In that sense, has a D wave type pattern, okay, because of that. Okay, and it has different, character in that sense. So we classified, for instance, assuming that there was no lattice, we looked at the Goldstone modes and all of that. So naively, it has an SO3 symmetry due to spin. In the absence of spin orbit is SO3 times SO2, which will be the internal space. But SO2, as I said, is actually the physical rotations. And in that sense, it will be broken to a point group symmetry once you couple that to the lattice. So many of the things, interesting features of these collective modes, are actually strongly affected by the fact that this is actually strongly coupled to the lattice, the physical rotation is said. Similarly, spin orbit will break these to a subgroup. Okay? So keep that in mind. So there are many possible mechanisms for this problem. Certainly Pomeranchuk is one of them, but again, as I say, it's a strongly coupled effect, but you can also get an symmetry breaking as in multi-band systems, so systems with more than one sublattice in the unit cell, as in the example that Raphael discussed. Okay, so there are many, again, the same phase can be realized in different ways, okay? So with the student, Rodrigo Soto Garrido, who's now on the faculty at Universidad Católica in Santiago de Chile, when he was a student, we decided, one of the reasons we were interested in the pneumatic, spin pneumatic, is because by then we realized there was something called a pair density wave, which is a state where the superconductivity is not translation invariant and behaves like what people call the Larkinov-Chinnikov state in the case of superconductors in magnetic fields, except that it does it without a magnetic field in this case. So it doesn't break time reversal because of that. Okay? So time reversal, okay? Doesn't break time reversal because there is no magnetic field, so it's invariant. Okay, so unlike the full deferral state, which spontaneously breaks inversion and time reversal because it's a spiral. Okay, so they have different symmetry. So you have to think about these two possibilities. And for that reason, even though we realized that if you have something with, so we looked at both cases. So we looked first at the simple case. Then I will give you the more complicated version related to what Raphael discussed. And so in this case, you can see that the upspin or the downspin Fermi surface is always nested. So you could always get a P wave instability here. Okay? So we said, we knew that you could also get P wave, but if you wanted to get something that spontaneously breaks translation symmetry when you pair, so you will want a singlet. So you have to do interband. So you have to say from the downspin here with the upspin there, and that will actually have a net momentum. Okay? So that was the idea. And here is actually richer. I'll come back to that in a moment. So we set out to look at the different susceptibilities. The triplet pairing susceptibility is always divergent because of nesting, has a logarithmic divergence. I'll come back to that later. In the singlet channel, you could look for S wave or D wave. The S wave, as usual, at least in the simple Fermi liquid setups, is just flat. There is this kink here, and then it decays. So there is no divergence. But in the D wave phase, the pairing susceptibility with the D wave 4 factor has a nice peak. And that peak gets bigger as the distortion gets smaller. So if you are very close, you are inside the altermagnet, but very close to the phase transition, let's call it the Pomeranchuk point if you wish, then in principle this is going to be very large. Of course, it's not divergent, but if you have some moderate coupling, it can compete with the P wave instability, which even though is always present, if the coupling for P wave is weak and this is moderate, they actually can compete with each other. Okay, so you can look at a scenario where you can break spontaneously the translation symmetry. We set out to look for analogs of essentially the pair density wave in this setting. Okay, so I was obsessed, I'm still obsessed with pair density waves, and this was my motivation at the time. Okay? On the other hand, in the beta phase, the situation is different. Okay, by the way, it is important that this is actually tuned by the distortion, in other words, by the altermagnetic order parameter. So the smaller the order, so you can think of the of this Pomeranchuk point where the altermagnet first appears as a complicated multicritical point. Because inside the altermagnet, in this regime, very close to the onset, this competition is actually strongest. Okay, so it actually leads to interesting phase diagrams because of that. Of course, as the distortion gets bigger, then the peak will get smaller. Yeah.
So just one, I think you mentioned, but I missed it. So for the D wave, that there's the peak. should I think of this as a log that is being cut off by the same scale delta?
In some sense, it is like that, yes.
I see. So
it's a cusp, actually.
Okay. So as delta goes to 0, both it diverges and moves to 0. Okay.
But it's a cusp, okay, that you see. It's not drawn as a cusp by an accident because it is a calculation. It's a cusp. On the other hand, in the beta phase, both the S and the D wave actually have the same cusp-like behavior, except that the D wave is stronger than S wave, but that's a quantitative difference. Okay? Okay, so then we decide to say, well, what are the possible superconducting phases you can get? This is a paper from about 2014. So we did a Gorkov type analysis. So we looked at the leading instability. You see big chunks of blue here. We didn't explore what happens inside these big chunks. It's a complicated problem. So we looked at the leading instability as you access the phase transition, as you access the phase. So you go, say in the case of the alpha phase, which is here, from a non-superconducting state, it turns out that the first singlet state you see is actually a uniform D-wave superconductor. Okay, it's allowed, and it's actually the one that dominates. Of course, it will have to compete with the P wave. Okay. Now, on the other hand, okay, at some point, this is rather complicated. It's a tricritical point. The transition becomes first order eventually. I don't know how much of that to believe is mean field theory after all, so one has to be careful with that. And then you begin to get phases that beg translation symmetry. The first one you get is a pair density wave, which is like a Larkin of Chinnikov type state, that actually, because of the nodal feature, and I want to see that, so these are these nodes in the altermagnet. The first place where that appears is along these nodes, and so it doesn't break that symmetry. So you may ask, and by the way, that's an important question, what about the FF type state, the spiral? At the quadratic level in the free energy, they are degenerate, but the quartic term actually prefers the pair density wave over the other one. Essentially, you're going to end up with two complex order parameters versus only one, and so you get more condensation energy in the pair density wave than in the FF type state. Okay, and so you begin with something which is unidirectional, so it's bidirectional, sitting here first. There's a small region where it remains bidirectional, eventually goes into a unidirectional pair density wave, and the direction begins to rotate as you increase the distortion. At some point, of course, it will go down to nothing, but by then you don't believe the accuracy of your approximations. Okay? So that's the case for that. Now, in the case of the beta phase, the situation is more complicated. Okay? So let me show here. We first looked at, here is assuming an S-wave form factor, so assuming that it's in the S-wave channel, and this is in the D-wave channel. The D-wave channel is rather similar. There is, again, a uniform D-wave. Okay, there is some issue about the nature of the transition. There is a pair density wave and a bidirectional here. In the S-wave channel is more complicated. In addition to a pair density wave, you get a triple helix. This is better than the double helix that we all have inside. Sorry, that's a bad joke. So it's a helical state, so it's a tridirectional helical state, essentially. We call it a triple helix. Interestingly, the physical review did not object to call that a triple helix. And then it goes into a bidirectional pair density wave and a tridirectional pair density wave. So you can see that you get the zoo of possible phases that are allowed. Okay, so it's actually quite a rich multicritical point. You need to think of this as some sort of multicritical point where many of these phases are in close competition, and depending on parameters, one or the other may be realized. Okay, so this is where we left it off. Yes? Sorry? Because there's a symmetry. There is a lot of symmetry that you can, many symmetries you can break. Okay?
Thank you.
Yes, Marcel here.
So It's more of a comment. So I think it's a bit misleading because what you label non-superconducting would actually be a triplet P wave, right?
It could be. It could be. I don't know. So as I said, this was done ignoring the P wave instability.
Yeah, but that has a logarithmic
Yes.
singularity.
Okay.
It would go P wave at infinitesimal.
Yeah, but the problem is if the couplings are not so small, then there is a competition. Of course, in the assumption that there was no P wave, that I could ignore P wave, this is the phase diagram. Okay, if you include a P wave, then it gets richer. Okay? And I'll come to that in a moment. Okay, so this is how we left it back in 2014, okay, a few years ago. At the time, it was, I mean, even today, I don't know, I say that to some extent this is a theoretical exercise, since, well, there are maybe one or two materials which are actually metallic. At the time, there was no even trace of any of these phases anywhere, so it was purely speculative, and it was an exercise to see whether this was a way to understand where you could get pair density waves from some reasonable mechanism. That was the motivation that was behind this. And you get more than what you wanted in reality. Okay, so we have recently begun to explore the problem in the context of microscopic models of altermagnets, in particular the Lieb lattice that was mentioned by several people. In particular, we use this Hamiltonian, this model that Raphael mentioned. The citation is here. I think the paper is recently been published in PRL, I think. Okay, so we use this model. Okay, we could have sat near the band touching point, but we decided not to. So we go to the regime where two of the bands, say the up spin band for the A sides and the B spin, down spin band for the B sides, for the two sublattices that you have here. These are the only two guys that are present. Okay, so you get, so essentially in that vicinity of that place, you get a band structure that, roughly speaking, looks like the one I mentioned before. Of course, this is a square lattice, so they're not going to be ellipses, so they will be squashed in different directions. So they have to satisfy the symmetries that the microscopic model has, but qualitatively it looks like the alpha phase or the altermagnet. Okay, so it closely resembles an alpha phase, and now we decide to take seriously the P wave channel. And we only consider the P wave channel in this case. Okay, so you can criticize me for why I didn't look for the singlet case. Okay, you will see that this is rich enough. Okay, so again, so this is the pair in susceptibility that is logarithmic divergent. This for Px and Py. It turns out that P plus Ip also has a log divergence and is actually stronger quantitatively in the other two. So it really wants to break time reversal spontaneously in some ways. Whether it does or does not depends on the interplay of these different bands, as you will see in a moment. Okay, so I'm going to, so the A site I'm going to assume has spin up and B has spin down. You can do it the other way around. Okay, so you're in the altermagnet, and then you can write down, so S as a label will be for A and B. I'm not going to carry the spin. Please remember the one has spin up, the other one has spin down. And the two basis functions are sine kx and psi ky. So you take this pair field and you decouple that as a linear combination in these different channels.
Maybe 5 more minutes or something?
Yes, that will be fine, yes. So the superconducting phase are represented by essentially 4 complex order parameters, because you get 2 complex order parameters for each sublattice now. So there are 4 possible superconducting amplitudes. So this is a rather complicated multi-component superconductor, okay? And therefore it's very rich because of that. Okay, even within this simple mode actually gives you some way to think about it. So you can parameterize that in terms of an amplitude and a phase. You can, this will be like the average amplitude for each sublattice and the relative amplitude. This alpha essentially is to parameterize the relative strength of the magnitudes of these pairing fields. Okay, so if you do calculations and you minimize energies, you find that it likes to have P plus Ip order, But in general, the strength of px and py are not the same for each band, for each case. So it's p plus ip, but essentially it's not isotropic except in one particular limit. So keep that in mind. So there's always this relative phase beta is pi over 2, okay, plus or minus, and that's the p plus ip. So unless alpha is pi over 4, then these strengths are different. Okay, so you go through the Landau expansion. Here is in its full glory. Okay, so you have 4 order parameters, complex order parameters. So you get the usual quadratic terms, the quartic terms, and various other biquadratic, but they're biquadratic terms. And there are terms, you can think of them as Josephson-like, that essentially coupled some of these superconducting phases through, not only through the amplitude, but also through the phase. It turns out that there are only 2 that are allowed, these 2, this one and that one. And it turns out that at the level of the simple model, there is a great deal of degeneracy left. There are a number of phases that are still degenerate. So we added some fluctuations. And let me come back to the model. So we looked at the effects of possible effects of nematic fluctuation, not nematic order. We don't want to break the sublattice symmetry. But we assume that there are some nematic fluctuations. They don't have to be divergent, but they have to be present. So essentially, nematicity here is to make the red and blue sides different. That's what that will break the point group symmetry. But if you assume there are simply density fluctuations here, essentially that will give you a handle for that. There is another one, which was mentioned, the complex, in the case of Kagome. You could also have loop-like order. If Chandra Varma would be here, he would be happy. But again, I will stay away from where the loop order exists. I will look at the effects of loop order fluctuations only. Okay? Loop order, of course, breaks time reversal in general, unless you do some sublattice effects and so on. So it turns out the last one, this last term, only exists when you include the loop order fluctuations. The other coefficients, you get corrections to TC from these nematic and loop order fluctuations as well. But in particular, say these 2 terms, particularly this.
What does it mean a Ginzburg-Landau coefficient only exists if you include loop current fluctuations?
Because there is an accidental symmetry that actually set it to 0. In the model.
Oh, yeah, you have a model, but this is a Ginzburg-Landau theory.
Of course.
Can do whatever it wants.
Yes, I know, absolutely. So the
you're
model actually...
So you're saying you're taking the M word and you wish to look at microscopic mechanisms?
Yes,
now. Okay.
That's what I did. I started with the model. But in that model, then there are accidental symmetries that makes essentially some of these coefficients vanish. And then you say, what are the simple things you can do? Okay. So it turns out in some cases, loop fluctuations and nematic fluctuations compete with each other.
Right.
Okay. In some cases, they don't. Okay. So they give you shifts. So in particular, most of these coefficients, they don't. But in particular, in this guy here, I think, and also in this biquadratic term, they actually compete with each other. One tends to be more, the loop order tends to make it negative, the nematic fluctuations tend to make it positive. And here I put the minus sign because in the case of loop order fluctuations, it's negative. Okay? So as you can see, you can get a lot of stuff from a diagram, from a phase diagram, from a Landau expansion of this type. Okay, so we explored at the level of mean field theory only the phase diagrams that you get. So let me start here, and the horizontal axis is a nematic susceptibility, so we use that to characterize the fluctuations. And this is temperature, so this will be the normal state. And we find here at least, you can see at least 5 phases. It turns out that there are hidden phases in this little corner here. So for instance, here phase 1, only delta AY has a non-zero expectation value, and here delta BX appears. So you can get progressively, depending which one of these other parameters develop an amplitude, you can go to 5 where all of them are present, essentially. Okay? And then you get various degrees of symmetry breaking associated with that. Now, if you look in the vicinity of this point, you discover that, in fact, there is another phase, and actually we have another example with still another phase there. So they depend on details. It depends on whether these two lines essentially will cross before they reach. By the way, the dotted line in mean field theory is a first order transition. The other ones are continuous, at least at the level of mean field theory. On the other hand, if I look at the case of loop fluctuations only, and this will be the susceptibility, what you get is a simpler diagram, which has this form. You go from this phase 5 to the phases 4 and 4 prime that only depend on essentially they switch around these two amplitudes. They're essentially the same phase. Okay, so the moral of this is that these states generally break time reversal. There are P plus IP states, and sometimes it's P plus IP for one, P minus IP for the other. So there is also that richness. And they also break point group symmetry, so they are nematic. Okay, so let me finish now with what's on the horizon. So you have essentially a very complex phase. So you have, when you think about superconductivity in these type of states, you have to include all of these possibilities. And this is primarily because of the multi-sublattice nature of this particular realization. The simple Pomeranchuk place is simpler because there are no sublattices there. But in this case, there is an unusual richness. Because these are multi-component superconductors, they host fractionalized vortices, and this is unavoidable. You can also host vestigial phases where you get higher order condensates. As in the case of paired density waves, here it will appear as well. These phase transitions, of course, is a two-dimensional systems, are going to become, as a function of temperature, there will be costless Thoudis-like. Okay, so much as in the cases that were studied. But you also get different types of vestigial orders that you can think about. So for instance, time reversal can be a vestigial order in this case. So you melt everything else, but you remain with the vestige. Is the Cheshire cut of this problem. The time reversal breaking remains and the other symmetries disappear, are restored. And similarly for nematicity. Now, the fact that some of these superconductors that you get here break time reversal suggests that they may actually be topological. Whether they are truly topological or not remains to be seen, but this is a good thing to explore. So as you can see, there is a lot of potential richness in this problem that I don't think has been studied in detail and is only being scratched at the moment. And this is a good moment to finish. Yep.
Thank you. So, like, how should I think about these vestigial phases? You said, like, something is partly melted, but you don't mean in terms of, like, domains, like spatial.
No.
So
it means, okay, is there a chalk here? Oh, here. Okay, so an example, I think people study that in the case of, for instance, of the iron superconductors. Okay, let me give you that as an example. It's the same story here. So imagine that I have a spin density wave, and it could have two possible ordering wave vectors, say pi 0 or 0 pi. Okay. So that breaks, people call it a stripe for historical reasons. I don't know why they call it a stripe, but it's two spin density waves. So you could take, let me call this one is pi 0 and this is 0 pi. You can look at an object okay, so this object breaks spontaneously the point, essentially the symmetry. The first one actually has two degenerate density waves or spin density waves pointing along the x or the y direction, whatever you want to call it. This state is oblivious to that, but breaks the symmetry of the lattice, the point group symmetry. So this plays a role of a nematic order parameter. So even though the expectation value of S pi 0 and S 0 pi may be 0, the magnitude is not, in general. So in this sense, it's vestigial. Okay?
Thank you.
And the same analysis can be done for these multi-component superconductors. Okay?
Thank you.
Okay.
Thank you very much. I was looking at your phase diagrams, just your previous slide, and between the first and the second, so basically what you're doing is you are basically
By the way,
blow
this
up.
is just, I enlarge this.
Right, this blow up here. So what you're telling us is that it's extremely rich. So that means that now, and basically here you are taking the Lip lattice model as a model. So now if we go, let's say we take the Kagome, it will be even more, right? So the richness, as soon as you put more sublattices.
Yes, and it also depends on parameters. For instance, even here, I didn't want to overwhelm you with phase diagrams, because these two lines may cross before they reach the first order line, or so there are bicritical points and tetracritical points. There are all kinds of things here. Okay. Now, this is you need to be careful that this is a mean field analysis, and there is a question how much will survive in the end. Some of these transitions may become first order for better reasons. Okay, so it's cannot be excluded, but it tells you that there are many possibilities, and it does depend on the microscopic physics actually.
Thank you.
So it's not the microscopic physics doesn't matter. Okay. Okay.
Yeah, thanks for the nice talk. You had two stories. One was that you had pair density wave states that were stabilized, and the other one you had this triplet, and you never mixed the two. And I just wanted to point out that one of the disappointments with the pair density wave is when you look at your scale, you needed something like the magnitude of the altermagnetic order to be comparable to the gap for this to survive. And in practice, this scale is much, much bigger than that. And it's interesting to ask how you can maybe increase the stability of these pair density waves to survive to much larger values of this. And I think one way you can do that is to allow the triplet to also coexist, because in other problems like FFLO, you can show that you can extend the range of pair density wave stability by a factor of 10 by allowing the spin triplet to coexist, and they are induced by one another in these states.
That's a good idea. Yeah, that's important. This was, as you can see, is a first pass, and it's rather naive. And I really need the crutch of being close to the Pomeranchuk point to actually make this even possible. Okay, that was at that level. I wanted to have a control parameter. There is no control parameter for Pomeranchuk, but the distance to this point plays the role of my small parameter in these expansions, essentially. If I need to go further away from that, then I need better physics. Okay, okay, thanks. Yeah.
Thanks. And, yep.
Eduardo, I wanted to ask if you... On? It's on? Now it's on? Eduardo, did you try to look also into P-wave magnets?
So,
did you try to look also into P-wave magnets? What superconducting phases can happen there?
to P-wave?
To P-wave, to the phases, alpha and beta phases with winding equal 1.
The problem with, okay, so I had the prejudice that the case with winding 1 was not allowed because of in the continuum is not allowed, it's unstable. I was told recently, I wasn't aware, that lattice effects may actually make it possible. And the answer is no, I have not.
Okay.
Okay.
Thank you.
By prejudice, I have not. Okay. That's an interesting question, actually. Yes. Yeah. Yes.
So very general question. So you mentioned for the nematic spin nematic, there is no Goldstone mode, right?
Due to lattice effects, yes.
Yeah. So Is there another elementary excitation? Is the symmetry breaking? Does it give rise? What's the signature of the symmetry breaking in terms of elementary excitations? Is there any?
Well, it's like a problem. You can ask yourself, suppose I give you a commensurate charge density wave versus an incommensurate charge density wave. The incommensurate charge density wave has a Goldstone mode, which is the sliding mode. Okay, it's a phase. In the commensurate case, that reduces to 5 or a few ground states, depending on the periodicity. So you will have several possible phases depending on what remains. In this case, it's usually C4, and the symmetry is just C2. There will be easing-like. Okay. But it's different in Kagome, it's different in the other systems. Okay, it depends on the.
So there is an interesting possibility. If you have, in the models that I showed in the Kagome, and I believe in the ones that Thomas showed, you actually get a 6-state clock model. And that one, if you're in 2D, you don't get a Goldstone mode, but you get a pseudo Goldstone mode because it's a dangerously relevant perturbation. So you do get some, you could get some very interesting.
It's better than that. It's simply that you get what people call a floating phase.
A floating phase, exactly.
Yeah, so you get a phase which is a critical phase. It's like, so you get two causaly Staulis transitions at the endpoints for Z6.
So if they were able to do this manganese telluride in a purely 2D system, you should see this critical phase and this Goldstone modes and so on. The manganese telluride would work the same way.
I mean, you need to
have
be
a 6-state clock model. You have 6 domains.
Okay, let me just give a word of caution. Okay.
3 times 2.
6. Okay, a great word of caution. Okay, let me caution about something here. Suppose that the system is not truly 2D, but is sort of layered and is quasi-2D. If you try to go from 2D to 3D, typically many of these systems actually become weakly first order, the phase transitions. And you lose this interesting regime. So the regime exists only if it is strictly two-dimensional. Okay? Or if you want the layers are so separated that it doesn't matter. Okay.
Can I have this?
Yes.
Sorry, I was wrong. They're right. Manganese telluride is easing. Apologies.
Easing. Icing.
Very simple clarification question. All these P-wave phases were S equal 1 phases?
Well, yes, it's a spin triplet. Okay.
Yeah, but you can have also the S equal 0, right?
Yes, you could. I didn't look at it.
So everything was S equal 1?
Because I assumed that I already had a particular realization of the alter.
So all these deltas are actually 3-component vectors.
No, they are one
in the spin
component.
space.
They all have spin up or spin down depending whether it's A or B. Okay, that's important.
So it's SZ, you have 4 components because it's SZ1 and -1. But because in the altermagnetic phase we split,
We don't have an example of Z equals 0. Okay.
more?
Maybe people want lunch. Talk first.
So I don't know, yeah. What's the best next talk or?
Okay. Thank you.